Ok, stiamo registrando e adesso facciamo lo sharing. Ah, ok. Ok, riuscite a vedere il mio schermo?
Sì, sì, lo vediamo.
Ok,
Sì, lo
oggi ho
vediamo.
cambiato browser, quindi vorrei essere sicuro che tutto funzioni. Allora, dunque, ieri nella ultima parte della lezione abbiamo cominciato a introdurre la QCD, la Quantum Chromodynamics, che è la teoria di campo delle interazioni forti, e in particolare, diciamo, ripercorrendo gli step già utilizzati per ricavare la lagrangiana di QED, abbiamo ricavato anche la lagrangiana di QCD. E abbiamo visto che, diciamo, sebbene la struttura, diciamo, sia analoga, ci sono ovviamente dei pezzi in più, è più complicata, e la ragione di questa complicazione sta nel fatto che SU3 è essenzialmente un gruppo di simmetria non abeliana. Non abeliana vuol dire che i generatori di SU3, che in particolare sono le tre matrici di Gell-Mann, non commutano tra di loro, ma seguono delle regole di commutazione ben precise che sono date in termini anche delle cosiddette funzioni di struttura, le structure function della QCD, quelle funzioni f, i, j, k, che sono delle quantità totalmente antisimmetriche e solo, come abbiamo visto in alcuni casi, assumono valori diversi da 0, in tutti gli altri casi hanno valori uguali a 0. Sulla base di ciò abbiamo quindi introdotto le derivate covarianti per la QCD, al prezzo ovviamente di introdurre anche qui dei bosoni di gauge. In questo caso non si tratta di un solo bosone, come nel caso del fotone in QED, ma di 8 bosoni, perché adesso diciamo, la dimensione del gruppo è 8, chiamati gluoni, e per ciascuno di questi abbiamo definito anche la proprietà di trasformazione, in modo tale da rendere gauge invariante la lagrangiana. Anche qui quindi abbiamo un termine in più rispetto al termine di QED, e anche qui abbiamo introdotto poi il termine cinetico, il termine del tensore di QCD G mu nu. La cosa, diciamo, la differenza rilevante che abbiamo visto ieri e che riprenderemo oggi è che, come conseguenza del fatto che la QCD di fatto è una simmetria non abeliana, i gluoni, che sono i bosoni di gauge, trasportano anche loro carica. Le cariche in QCD sono le cariche di colore, abbiamo visto ieri, le riprenderemo anche oggi, quindi rosso, verde, blu, e i gluoni, a differenza del fotone, trasportano carica, il che ha come conseguenza una differenza sostanziale rispetto alla QED, cioè il fatto che, sebbene i fotoni tra di loro non possono interagire perché appunto sono neutri dal punto di vista della carica elettrica, i gluoni invece possono anche interagire tra di loro e dare origini a interazioni a 3 e a 4 a vertici a 3 e a 4 gluoni, per esempio. Okay? E questo chiaramente ha tutta una serie di conseguenze in quella che è proprio la dinamica delle interazioni forti, come vedremo anche meglio oggi e domani. Ok, quindi adesso andiamo avanti. Fatemi giusto verificare una cosa. Oh, si è aggiunto qualcun altro. Va bene. Allora, andiamo avanti. So, the three color states of QCD are red, green, and blue. Okay. Now, similarly to QED, where particles and antiparticles have opposite electric charge, okay, the same thing happens here. So the antiquarks carry the so-called anticolors, which is the opposite color charges. And in fact, we can define the anti-red, the anti-green, and the anti-blue in the same way. So this table here helps to understand better. So here we have the three colors, the three fundamental colors, which are red, green, and blue, okay, which are fundamental in the sense that they are pure combinations of colors. Red is pure red, green is pure green, blue is pure blue, okay? And here we use now essentially the same convention that is used in computers or in printers, okay? Now we can define the anti-colors, okay? So the anti-red, okay, is a combination where the red is 0, but then we have both green and blue. So when you combine green and blue, you get the anti-red here, which is this color here, cyan, okay? The anti-green, okay, is a combination where there is no green and there is red and blue. So red and blue goes here, so this is our anti-green, that is magenta. And finally, the anti-blue is a combination where there is no blue, but then red and green, and this corresponds to the yellow, and here we are, okay? Then if we now sum up all the three fundamental colors, red, green, and blue, we obtain the white, as we know from basic colors, okay? White is, of course, in a sense, absence of colors, okay? And on the other hand, the opposite of white is black, okay? Now, why all these become relevant, okay? This we will learn better today. Let's see what happened when we combine three quarks into baryons, okay? So baryons, as a result of QCD, are made by a red quark, a green quark, and a blue quark. So when you now sum up the three color codes, so it's 100 plus 010 plus 001, you obtain 111, which is the white. That means that all baryons are colorless, or in other words, they do not carry color charge. Mesons, similarly, they consist in combination of a quark and anti-quark, so of a color and its anticolor. So either red anti-red, or green anti-green, or blue anti-blue. Actually, it is a combination of these three. So, for instance, if you consider the red, okay, you sum up 100 plus 011, again, you obtain the white. So again, mesons are colorless objects, okay? And in general, hadrons are colorless objects and are also called color singlets. The meaning of color singlets will be clear later on. Now, let's now concentrate ourselves on the quark-gluon interaction, okay? So as we have seen for QED, the interaction term in the Dirac equation for an electron in electromagnetic potential is of this form here, okay? Where GE is essentially the charge of the electron, which is nothing else than the square root of the fine structure constant, okay? And what is put here in black, minus IgE gamma mu, is, if you remember, the vertex factor of QED. Now, we have to do something similar for QCD, okay? So in QCD, the analogous term would look like this, okay? Where now we have an additional index alpha that runs from 1 to 8, because we have 8 generators, okay? And GS is now square root of alpha S, which is the strong coupling constant, okay? And what is here in bold black is now the QCD vertex factor, okay? So you can compare now the QED vertex factor with the QCD vertex factor. And then, of course, here we have the photon, and here we have the 8 gluon fields. Now, so let's make this comparison. So apart from the different coupling constant, which is obvious, one is electromagnetic and the other is strong, the quark-gluon interaction only differs from the QED lepton-lepton interaction in the appearance of these 3x3 Gell-Mann matrices right here, okay? And these matrices, as we will see, they act only on the color part of the quark wave function. This will be clear in a moment. So the color degree of freedom can be incorporated in the quark wave function by simply multiplying the quark spinor, the usual spinor U, for instance, solution of the Dirac equation, times the color vector or color wave function, okay? So in QCD, we will not just use the spinor, but the spinor multiplied with the corresponding color vector, Ci, where I can be 1, 2, or 3. So C1 corresponds to red, is 1, 0, 0. C2 corresponds to green, 0, 1, 0. And C3 corresponds to blue, 0, 0, 1. Okay. Now, let's see now how this works when we want to calculate a current in QCD. Okay. So let's consider this quark-gluon vertex. Okay. So we have an incoming quark that radiates a gluon and then results in an outgoing quark. Here we have P1 and P3 are the four momenta of the initial and final state quark. Okay, mu identifies the vertex, and I and J identify the color of the incoming quark and of the outgoing quark, respectively. Okay, so now we want to calculate the current at this vertex, and we essentially apply the Feynman rules, but now also including color. Okay, so now, for instance, we start from the final state quark. So this comes as an adjoint spinor with free momentum P3, this guy here, attached with its own Hermitian conjugate color vector, J, Cj, where J is the color of the outgoing quark. Then we have the QCD vertex factor, okay, which includes the Gell-Mann matrices. And then we have the initial state wave function, let's say, which is again a combination of the initial state spinor, U of P1, combined with its color vector, where I is the color of the initial quark. Okay. Now, here we have essentially two different matrices. Okay, a 3x3 matrix, which are the Gell-Mann matrices, and 4x4 matrices, which are the Dirac matrices. Okay, so the 3x3 Gell-Mann matrices act only on the 3-component color states, so on the C states, whereas the 4x4 Dirac matrices, as usual, act on the 4-component Dirac spinor, so the U or U here, U bar. Okay, and so we can actually factorize the color part in this current. Okay, so we can just rewrite these as -1/2 IJS. Okay, so we just put all this constant on top of everything, and then we collect the color part, that is the Hermitian conjugate of CJ, the Gell-Mann matrices, and then the CI vector in the initial state. And then what remains is the usual vector current, just like the same we have in QED. So U bar, gamma mu, U. Okay. And then we can also write this color term in a compact way, like lambda alpha JI, okay, which is essentially what is written here inside the square parentheses. And this is just a number. It is actually a specific element of the Gell-Mann matrices. In particular, it is the jth element of the gamma alpha Gell-Mann matrices. So it's a number, okay? And so this is how the current for this quark-gloon vertex would look like in QCD. Okay. Now we can compare with the QED vertex. So here we have the electron photon. Here we have the quark-gluon vertex. Okay. So the structure is, of course, the same. Okay. So we have the final state wave function, the vertex factor, and the initial state wave function. The additional thing is that now here we have also the color vectors, and we have the Gell-Mann matrices acting on them. Okay, and so when we write in the compact form, we can now compare the final form. Okay, and apart from this coefficient here, which of course is different because the coupling constant is different, and also because we have this additional number here, then the rest is the same. Okay. And since the rest is just a standard vector current, and we have shown for QED that if the current is in the form of a vector current, then the parity and charge conjugation are conserved, then this also applies to QCD. So given that the current has the same structure as QED, it is just a standard vector current, then one can immediately show that also for QCD, parity and charge conjugation are conserved. Okay? We proved this formally for the case of QED, but clearly the demonstration is the same. Now, this was about quark. What about now anti-quark-gluon vertex? Okay, so now we write in this way, the arrow point backward in time. This is the convention in the Feynman rules, as you know. Okay, so if you remember the convention to write the current, we have to move now in the opposite direction from the direction of where these arrows are pointing. So now in this case, the adjoint spinor is the one of the initial state, anti-quark. So it's now a V spinor because it's an anti-quark spinor with P1 because it is initial state, with its own Hermitian conjugate vector color vector CI, where I is the color in the initial state, actually anti-I. Okay. Then we have the standard QCD vertex factor, and then we have now the final state here. Okay, again in terms of the anti-fermion, so anti-quark spinor. Then we can work out this in a similar way as we did before. So we can factorize the color part altogether. This we can write in a compact way, okay, in terms of the Gell-Mann matrix element. And this is what we obtain now. So the only difference is now that the vector current is written in terms of the anti-quark spinors, okay, and the initial and final state are inverted here. Now, a few words about the gluon propagator, okay. As we have a photon propagator in QED, of course, we would have also a gluon propagator in QCD. And the shape of the gluon propagator is this one. So it is exactly the same as the one of the photon, okay? Plus, in addition, this delta AB, okay? And this delta function ensures that the gluon of a type A, which is emitted at the vertex mu, is the same as that absorbed at the other vertex, okay, the vertex nu. And this is otherwise not obvious in QCD because gluons can interact among themselves with the triple and quartic vertices, okay? So in order to avoid that you start with a gluon and you absorb a different gluon, you have to apply this delta function here, okay, on the propagator. Otherwise, all the rest is the same, okay? You have the metric tensor and you have the squared transfer momentum here. Mi fermo un attimo. Chiaro fin qui, ragazzi?
Sì.
Ok. Va bene, diciamo, vado forse un po' veloce, però diciamo, di fatto stiamo ricalcando gli step che abbiamo già visto in QED. Chiaramente ci sono delle complicazioni maggiori qui, però diciamo, la procedura è chiaramente la stessa. Se vado troppo veloce, rallentatemi al solito, ok?
Va bene.
Ok. Now, back on the fact that, on the difference between QED and QCD. So QCD is a non-abelian theory, okay? And this implies that the gluons must carry color charge, as we mentioned before. And more specifically, in order to allow for color conservation at the vertex of any Feynman diagram, gluons must carry simultaneously both color and anticolor. So quarks carry color, antiquarks carry anticolor. Gluons must carry simultaneously a color and an anticolor in order to conserve color charges at the vertex, okay? And this becomes more clear in this example here. So let's consider this strong quark-quark scattering, where essentially we have in initial state a red quark interacting with a blue quark through the exchange of a gluon, and then in the final state the colors are swapped. So we have a blue quark here and a red quark there. And this we can visualize in terms of the color flow in this diagram here. So the red, okay, flows in this way, and the blue flows in this other way. And then we can split our Feynman diagram, if you remember, in the two different time ordering diagrams, okay? Essentially, the Feynman diagram is the combination of the two, is the sum of the two. So in the first case, a blue quark emits a blue anti-red gluon, okay, in the bottom vertex. The gluon is absorbed at the upper vertex, okay? The anti-red annihilates the red, and the blue color proceeds like this. The opposite time ordering is the one where now in the upper vertex, a red quark emits a red anti-blue gluon, okay? The anti-blue, the gluon is absorbed at the lower vertex, the anti-blue annihilates the blue, and the red proceeds, okay? The sum of these two time ordering, which are not physical, because as we've seen in QED, we cannot distinguish between them experimentally, okay? The sum of the two is the real process, okay, which is represented by this Feynman diagram. So this explains why you need to have both charge and both color charge and anti-color charge in the gluon. Okay. Now, more precisely, we can have the following 8 color anti-color combination for the gluons. Okay. So the gluons form an SU3 octet of colored states in this way: red anti-green, green anti-red, red anti-blue, blue anti-red, green anti-blue, blue anti-green, and then we have these two other combinations: 1 square root of 2, red anti-red minus green anti-green, and 1 square root of 6, red anti-red plus green anti-green minus 2, blue anti-blue. And if you remember, the structure of this color is exactly the same we already had in SU3 flavor, now considering not the colors, but the quark flavors, okay? So there we had UD bar, DU bar, US bar, SU bar, etc. Exactly the same algebra, okay? In particular, you see also in the bottom now the corresponding mesons, okay? So these are the mesons of the octet. You see that the structure of the SU3 group is clearly the same, okay? Differences, as we mentioned already, is that now we are considering colors. Before we were considering flavors, and SU3 flavor is an approximate symmetry, whereas SU3 color is an exact symmetry, okay? Now, of course, there is a precise correspondence between the 8 gluons and the 8 SU3 generators, so the 8 Gell-Mann matrices, okay? And the correspondence is given here. So the lambda 1 and lambda 2 corresponds to process where gluons, red anti-green or green anti-red gluons are exchanged. The lambda 4 and lambda 5 corresponds to processes in which red anti-blue and blue anti-red gluons are exchanged. Lambda 6, lambda 7, where green anti-blue and blue anti-green gluons are exchanged, and then lambda 3 and lambda 8, when gluons with this combination of cores are exchanged. Okay. Now, let me just take as an example these three, which are easy to represent also graphically. Okay. So each row corresponds to each of these rows here. Okay. So in the first row, we have a red quark that turns into a green quark by emitting a red anti-green gluon. Okay. So we are here. Or the opposite way, where a green quark becomes a red quark with emission of a green anti-red quark, and we are there. And the same for the other two, okay? So also here, the colors, real colors, allow to, of course, to visualize better the flow. In particular, let me take you an example. The gluon corresponding to the lambda 4 generator can only contribute to interactions involving the following changes, either red into blue or blue into red, and none to any other combination of colors. Okay, so let's see this more explicitly on the board. Vediamo se parte qui. Partita. So this is like 1. Okay, let's indeed calculate the this matrix element. So we start from red, lambda 4, blue. Okay. This we can also write as red, Hermitian conjugate, lambda 4, and blue. And then we can also replace the red and blue symbols with the C1 and C3 color vector, which are exactly the same. So it's C1 daga, lambda 4, C3. Now let's make all these explicit. So the C1 Hermitian conjugate is 1, 0, 0. The lambda 4 Gell-Mann matrix is 0, 0, 1, 0, 0, 0, 1, 0, 0. And then we have our C3 vector, okay, the blue, which is 0, 0, 1. Now, the first we copy, and then we make the product of the matrix with the vector. And if you do so, it is absolutely trivial. You obtain 1, 0, 0. Okay, and so overall, when you multiply now these two vectors, you obtain 1, which is different than 0, and which is absolute, of course, fine. Okay, so we are now showing that the lambda 4 matrix responds to a gluon exchange between process with the red and between red and blue. Let me make also a note here. So back here to this point, this we have written also in a compact way, if you remember, as lambda 4, 1, 3. And in fact, this corresponds to the element of the first row, third column of the lambda 4 Gell-Mann matrix, which is 1. So the one that we obtain is exactly this matrix element here. Now, let's work out the opposite process. Now, a blue through a lambda 4 gluon becomes red, or vice versa, whatever. So this is blue daga, lambda 4 red, which is equivalent to C3 daga, lambda 4 C1. And so now we have 0, 0, 1. Then the Gell-Mann matrix is the same, 0, 0, 1, 0, 0, 0, 1, 0, 0. And then we have our vector, which is now the red, so 1, 0, 0. We go on, so 0, 0, 1. You multiply the matrix with the vector, and you obtain now 0, 0, 1. So you take the product, and you obtain again 1, which is different than 0. And again, we are happy. This is what we expect. Again, this guy here is the lambda 3, 1, 4. So it is now the element of the fourth Gell-Mann matrices arising from the third row, first column. So this guy here. Let's now try a different combination. So suppose we want now to use the gamma 4 to exchange green to red. Okay, so we do the same, G daga, lambda 4, red, that is C2 daga, lambda 4, C1, that is 0, 1, 0, same matrix, 0, 0, 1, 0, 0, 0, 1, 0, 0, and now we have 1, 0, 0. So it's 0, 1, 0, and now we have 0, we have 0, 0, 1 when you make the product. And now, as you would expect, this is exactly 0, okay? So this color combination does not contribute to a corresponding current. Again, this is the lambda 4 to 1. So it is second row, first column. So this 0 here corresponds to this matrix element there, okay? So we have seen that C2 daga lambda 4 C1 is 0. That is when we want to use the lambda 4 generator to mix green and red, okay, which should not happen. And when we in fact plug this into the corresponding current, so we have JQ is equal to minus 1/2 IGS C2 daga lambda 4 C1, and then we have our vector current UP3 gamma mu UP1. Since this guy is 0, this current is overall 0. So it does not contribute at all in the matrix element of the process, okay? Ok, chiaro ragazzi?
Sì, stavo scrivendo, scusi il ritardo
Ok.
della risposta.
Benissimo. Quando avete tutti copiato, ditemi così passo avanti alla slide.
A posto.
Ok, tutti a posto?
Sì, grazie.
Benissimo. Ok, allora qui apriamo una pagina nuova e torniamo qui. Ok, so this hopefully is clear now. Now, in the calculation of the matrix element of any QCD process, one needs to account for the different colors of the quark and the gluons that can contribute. Okay, so let's consider as an example this QCD scattering between an up quark and a down quark. Okay, suppose that the up quark comes from the up quark and the down quark come from two colliding protons respectively. Okay, and they scattered one of the other strongly, so through the exchange of a gluon. So the exchange gluon is labeled by A and B. So A here and B there. And the delta AB in the propagator ensures that the gluon at the vertex mu and nu is the same. The incoming quark colors are labeled I and K. So the incoming quark has for momentum P1 and color I, and the incoming D quark has a for momentum P2 and color K. The outgoing quarks colors are J and L. Okay, so these outgoing up quark has for momentum P3 and color J, and this outgoing D quark has a for momentum P4 and the color L. Okay, and so the color flow in the diagram corresponds to IK in the initial state to JL in the final state. Now, in the strong quark-quark scattering process, the color of each quark involved is equally likely, equally probable to be either a red, a blue, or a green. And this is also the sense of the fact that the SU3 color symmetry is an exact symmetry, okay? So the three colors for each quark playing in this diagram are the same. And therefore, in total, we have 3 to the 4 color combination from the quark. Okay, we have 4 quarks, each can take 3 colors, times 8 different possible gluons that can be exchanged. And this overall results in 648 distinct combinations of quark colors and gluons that can potentially contribute to this process. It is a huge number, but we are lucky because the effect, as we will see, of summing overall the color and the gluon combination at the end will be absorbed into just one single average color factor, just one number, okay? And let's now see how this works. So let me first start with deriving the matrix element for the strong quark-quark scattering. So let's move back to the board. So we want to calculate the matrix element of the up-down strong scattering. This is page 2. Okay, so let me draw the Feynman diagram. Okay, so we have an incoming U quark with for momentum P1 and color I, an outgoing U quark with for momentum P3 and color J. Then we have an exchanged gluon, and then we have our lower vertex. So this vertex we call mu, and a gluon is emitted. This vertex we call glue, and a B gluon is emitted in general. Then, of course, the two must be the same. Now we have the D quark here, the D quark there, for momentum P2, color K, for momentum P4, color L. Okay, so we put all the relevant information in this Feynman diagram. And now we have to calculate the matrix element by using the standard Feynman rules. So if you remember, we proceeded much like the way we did for the molar scattering. So we start with the minus I mFi. And this is, so let's first calculate the current at the upper vertex. So we have the adjoint spinor of the up quark P3 with its Hermitian conjugate color vector. Then we have the vertex factor I, GS, gamma mu, 1/2 lambda alpha. And then we have the the initial state, so CI U spinor with for momentum P1. Then we have the gluon propagator, this minus, so this times minus I G mu nu delta AB divided by Q square. And then we have the current at the lower vertex. So this is a U bar P4 C daga L minus I GS gamma nu. Now we are in the nu vertex. 1/2 lambda. So let me call this A and this B, not alpha and beta, but A and B to be consistent. And then we have the CK U P2. That's it. Okay, so these are the three main pieces: the current at the upper vertex, the propagator of the gluon, and the current at the lower vertex. So now, as we learn, we can factorize the color part for the two, in the two currents. So for the upper vertex, we have CJ daga, lambda A, C1. And then we have our current, so U bar P3 minus 1/2 I GS gamma mu. And then we have U of P1. Then we have the gluon propagator. For the moment, let's just copy it. I G mu nu delta AB Q squared. And then we have times the second part, which we also factorize. So it's C daga L lambda B C K times Q bar P4 minus 1/2 I GS gamma nu U P2. Now, let's now merge.
Prima di
Sì,
andare
dimmi.
avanti, nella seconda corrente,
Sì.
lei ha scritto di nuovo U. In teoria è il quark down, però. no?
Sì, allora U è generico come spinore per fermioni.
Ok.
È la soluzione della questione di dire, che poi chiaramente uno sarà, bisogna mettere un pedice se vuoi U di U e U di D,
Ok.
però ho usato U per dire che è lo spinore, ok?
Ok, va bene.
Okay. Okay, now let's collect and merge all the color parts. So first of all, we put outside the constant G strong square divided by 4. Then here we have lambda JIA, now written in the compact form. Then we have the delta function, delta AB. And then we have the lambda LKB. And what remains is U bar P3 gamma mu U P1 minus I G mu nu divided by Q squared and U bar P4 gamma nu U P2. So let me note you that all this part here is essentially the QED analog. So all this part is exactly what you have in the molar scattering. Okay, the difference is what you have on top of this. Okay. So this was minus I M Fi. Let's now multiply by minus I, divide by minus I. So the matrix element, the transition matrix element MFI, is now given by minus GS squared divided by 4. Now we apply the delta function, so A and B becomes the same. So this is lambda JIA times lambda LKA, okay? So the delta is acting here, sorry. So now we have both A. Then we have G mu nu divided by Q square, and then we have the two vector currents. So U bar P3 gamma mu U P1 times U bar P4 gamma nu U P2. Now let me define a new quantity, which is the quantity capital C IK into JL, that is defined in this way. So 1/4 of the sum for A that goes 1 to 8 of lambda JIA lambda LKA. This quantity we call the color factor. And so in terms of the color factor, we can now write the final result as MFI equal to minus GS squared. We absorb now the factor of 4 into the color factor. So now we have C of EK into JL, and then we have G mu nu divided by Q square, and then we have the two standard vector currents. I will not copy them again.
Prof, scusi, mi sono perso un passaggio. Perché le due lambda hanno lo stesso esponente A e non B?
Allora, non è l'esponenziale, è un indice, lambda A,
Ok.
lambda A. Siamo partiti da un lambda A e un lambda B, ma abbiamo applicato adesso la delta. La delta
Ok,
ti impone che le due devono essere uguali, altrimenti fa 0.
ok. Grazie, scusi.
Niente, per carità. Allora, ditemi quando ci siete, così torniamo alla slide.
Ok.
C'è qualcuno che sta ancora copiando?
Io ci sono, ho fatto.
Ok, allora se ci siete tutti possiamo adesso tornare
Sì,
dall'altra
ci sono.
parte. Ok. Torniamo dall'altra parte. Okay. So this is the result that we just obtained. Okay. Now, if you now compare this with the matrix element of the molar scattering in QED, so electron scattering mediated by a photon, then you see that there are lots of similarities. Okay, so the molar matrix element is reported here. Okay, where again the GE coupling constant is nothing else than the electron charge. Now let's compare the two. And in particular, the QCD matrix element for a particular combination of quark cores can be obtained from the matrix element of the molar scattering by simply replacing the coupling constant, of course, and by multiplying by this color factor. Otherwise, they are the same. Okay, and the color factor accounts for the sum over the 8 possible exchanged gluons and all possible initial and final state color combinations. Okay. Now, each of the individual color factors can be associated with the exchange of a particular type of gluon, okay, and in such a way that the color charge is conserved at each vertex. And let's now see how this works. So, if you remember, we have 4 quarks, each can take 3 possible colors, okay, so the 3 to the 4 possible combination of the colors, I, J, K, L, can be grouped into 4 categories. The first category is the simplest one, okay, where all 4 colors are the same. Red, 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 okay? And so the color index are the same, 1, 1, 1, 1. The second category is the one where the 2 initial state quarks have different colors, but they do not change color. So we have red, blue in the initial channel and also red, blue in the final channel. So the color index are 1, 3, and 1, 3. The third category is where the 2 initial state quarks have different colors and they exchange color. So red, green becomes green, red, okay? And the last one is the category where all 3 colors are involved. We have red, blue, blue, and green, okay? Now, let's consider the first category. In the first category, we have essentially a red, red that goes into red, red. So in the upper vertex, okay, we have the C1 daga lambda alpha C1 for the mu vertex that we can write compactly as a lambda 1, 1 alpha. And in the lower vertex, the nu vertex, we have again C1 lambda C1. So here, the non-zero contributions arise only from the lambda 3 and lambda 8 Gell-Mann matrices because these are the only matrices that have non-zero values in the 1, 1 element. That is exactly what we want. You remember these 2 indexes give us the element of the matrix. So these are the 8 matrices, and the lambda 3 and the lambda 8 are the only ones that have the 1, 1 element non-zero. So the only one that contribute to this process, okay? In particular, lambda 3 and lambda 8 corresponds to this combination of colors. Okay, so the gluons carrying this combination of colors and anticolors, as was shown before. So let's now calculate the color factor for this first category. So I go back here. Page 3. So let me just rewrite here the 2 relevant Gell-Mann matrices. So the lambda 3 is 1, 0, 0, 0, minus 1, 0, and 0, 0, 0. And the lambda 8 is 1 over square root of 3 times 1, 0, 0, 0, 1, 0, 0, 0, minus 2. Okay. So the color factor now, we want red, red into red, red for this first category. That is C1, 1 into 1, 1. That is 1/4 sum from A, that goes 1 to 8 in general, of lambda 1, 1A, lambda 1, 1A. And out of the 8 possible Gell-Mann matrices, only those 2, the lambda 3 and the lambda 8, contribute here. So this is 1/4. And then we have lambda 1, 1, 3, lambda 1, 1, 3, plus lambda 1, 1, 8, lambda 1, 1, 8. I'm just making explicit the sum where only 2 terms contributes. So this is 1/4. Now we take the matrix element, so lambda 3, 1, 1 is 1 times 1, plus lambda 8, 1, 1 is square root of 3, 1 square root of 3. So overall we have 1/4, 1 plus 1/3, that is 1/4 times 4/3, that is 1/3. Ok? Quindi questo è il color factor nel caso in cui stiamo scambiando rosso-rosso in rosso-rosso, quindi non c'è nessuno scambio di fatto di colore. La prima categoria. E risulta un numero pari a 1/3. Now, let's go back to the slide. And due to the SU3 symmetry, which is exact, the same value, okay, arise when instead of red, you do the same for green and blue, okay? So all these three cases belong to the first category because there is just one color involved. And for all cases, due to the SU3 symmetry, you get exactly the same result, 1/3. Let's now move to the second category. Now it's red-blue into red-blue. So in the upper vertex, we have C1 lambda C1, so alpha 1 1 alpha, lambda 1 1 alpha. In the lower vertex, now we have the blue, so it's 3 and 3. So it's C3 daga lambda alpha C3, and this corresponds to lambda 3 3 alpha. So we do the same now. We check all our 8 matrices, and we realize that only the lambda 8 Gelman matrix is relevant here because it is the only one with non-zero values in the 1 1 and 3 3 element simultaneously. Okay, so it's the only one having this term and this term, this element, not zero simultaneously. And so now we calculate the color factor for this category 2. So we go back here. So the lambda 8 we have already. Now we want to calculate C of red-blue into red-blue. That is 1/4 sum A 1 to 8 lambda 1 1 A times lambda 3 3 A. Okay, one for the upper vertex, one for the lower vertex. We have only one contribution in this sum because only the lambda 8 Gelman matrix contributes here. So this is simply 1/4 lambda 1 1 8 times lambda 3 3 8. So we now pick up the matrix element 1 1 and 3 3, and this is 1/4 1 over square root of 3 times minus 2 divided by square root of 3. And it is 1/4 minus 2/3, that is minus 1/6. All right. So back on the slide. Again, we exploit the SU3 color symmetry. So if this holds for the red-blue, this must also hold equally for the other combinations, red-green, green-red, green-blue, blue-red, and blue-green. So for all these cases, which belong to the second category, we obtain minus 1/6. Now we do the same exercise for the third category, okay? Now we have red-green that goes into green-red. So in the upper vertex, we have C2 lambda C1, and in the lower vertex, we have C1 lambda C2. Again, we check all the matrix elements, and we found that only lambda 1 and lambda 2 have simultaneously non-zero values for the 2 1 and 1 2 elements. In particular, if you remember, lambda 1 and lambda 2 correspond to exchange of red anti-green and green anti-red gluons. So again, back on our slide. Here I need to write down the lambda 1 and lambda 2. So it's 0, 1, 0, 1, 0, 0, 0, 0, 0. The lambda 2 is 0 minus I 0, I 0, 0, 0, 0, 0. And so the color factor for red, green into green, red is 1, 4, sum from 1 to 8 of now lambda 2, 1a times lambda 1, 2a, and only two terms contributes because only the lambda 1 and lambda 2 matrix have non-zero values here. So it is lambda 2, 1, 1, lambda 1, 2, 1, plus lambda 2, 1, 2, lambda 1, 2, 2. Now we replace the numbers. Is 1/4, 1 times 1 plus minus I times I. That is 1/4, 1 plus 1. That is 1/2. Ok? Domanda?
No?
Ok. Allora, torniamo sulla slide. Again, we exploit the color symmetry. So for all these combinations of color exchange, the color factor will be exactly 1/2. Now we are left with the last category, okay? The one that mixes three colors. So here we have red into blue, blue into green. So in the upper vertex is C3 lambda C1, and the lower vertex is C2 lambda C3. However, when you now look at the 8 Gell-Mann matrices, we would find none of them having simultaneously the non-vanishing 3-1 and the 2-3 elements. None of them. And as a consequence, the color factor for this color combination that involve the three colors is 0. Okay? And the result should be expected because in this case, no gluon exchange can ensure color conservation at the two vertices. All right. What about now anti-quark or quark anti-quark scattering? Okay, so essentially the same happens here. So this is the anti-quark scattering by gluon. So we have now the anticolor involved, and these are now the corresponding color factor for the corresponding anticolor. Okay. Now the difference is that now we are swapping the order because if you remember the mnemonic rule that I gave you before in QED, you have now to start from the incoming antiquark and going back to the outcoming. So the order of this index is reversed to the case of quarks, and so you are essentially reversing rows with columns in the Gell-Mann matrix. Okay. Then we have the mixed case. You have scattering a quark with an antiquark, so you just swap one of those and not the other. And then you can also have this kind of S-channel annihilation processes, okay, which are given in this way. Now, from the properties of the Gell-Mann matrices, it turns out that the same color factor are obtained for quark-quark, quark-antiquark, and antiquark-antiquark scattering. So easy, very easy, okay? So for instance, we have seen that for red-red into red-red, we got 1/3, and this also applies to red-anti-red, or anti-red-anti-red into anti-red-anti-red. Okay, for red-green, we got -1/6, and the same for these combinations. And for red-green, green-red, we got 1/2, and the same applies to these combinations. Okay, and concerning the S-channel, okay, we have again all these three combinations, which account. So we have 1/3 for the first combination, sorry, 1/2 for the second, and -1/6 for the third combination. Okay. Of course, one can compute them again, but ok, non abbiamo bisogno di ripetere l'esercizio, avete capito come si calcola. Okay? Le formule sono queste che trovate qua sotto. So now, in the strong quark-quark scattering process, the color of each quark involved is equally like to be red, blue, and green, as I was saying before. Therefore, the 9 possible initial state and the 9 possible final state color combinations are all equally probable. And so we have to take all of them into account, okay, in order to describe our physical process. So for a particular initial state color combination, the cross-section will be given by the sum of the squared matrix element for each of the 9 possible orthogonal final state color combinations, okay? So how do we put everything together? This you know already. We have done for the spin, now we do for the color, okay? So we've done for the helicity combinations, if you remember, okay? Now we do the same for the color combination. So the possible color combinations are accounted for by the color average sum of squared matrix elements. So this is our average square total matrix elements, and now we are summing over the initial state colors, the final state colors, averaging over the initial state core, so we have 1/9, and summing all these partial squared matrix elements. So for each of these color combinations. Okay, so the sum runs over all possible initial and final state cores, and the factor 1/9 essentially comes from the average over the 9 possible initial state combinations. Now here we have the full, let's say, matrix element of the process, but of course this average only apply to the color part, and we can factorize if you remember. So when we restrict ourselves, essentially what we have to calculate is this sum here, okay? So it's essentially the sum over the squared color factors divided by 9. Now we use the value that we're calculating for all the possible color combination, okay? So when we sum all these, we get 3 times 1/3, 6 times 1/6, 6 times 1/2. We do the calculation and we obtain just a simple number, 2/9, okay? So the effect of the total 648 possible combination of quark cores and gluons at the end can be replaced by just a simple average number, so an average color factor of 2/9, okay? And it is also the same for the anti-quark and the quark anti-quark scattering. And this applies to the T-channel and the S-channel processes. So things are complicated, but at the end they become very, very simple. You just have to take into account this average factor. And so we can now compare, indeed, the molar scattering with the quark-quark strong scattering cross-section, okay? So this is the cross-section for the molar scattering in terms of the Mandelstam variables, in terms of S, essentially, that we derived in QED. And this is the corresponding strong quark-anti-quark cross-section. What are the differences? First of all, here S is the squared center of mass energy of the 2 incoming electrons. And now S hat is the center of mass energy of the colliding Q-bar system. Of course, we cannot provide a beam of quarks and the target of quarks, but only a beam of protons or hadrons and the target of hadrons. And so the beam energy will be those of the hadrons, not those of the quarks. And so the center of mass energy will be, of course, different. And this will be understood better in the next week. Okay. Then the other difference is that, of course, we have to exchange the coupling constant. So the structure function becomes now the alpha strong. And the last thing is that you have to apply this factor 2/9 to account for all, in average, to all possible color-quark combinations and all possible gluon exchange. Ok? Possiamo fermarci qui. Scusate, possiamo fermarci qui. Se avete domande, fate pure. Prima per una pausa. Tutto chiaro?
Può ripetere un attimo?
No, sì, tutto chiaro, non ci sono domande.
Dai,
allora, dunque, scusa, cos'è che devo ripetere?
Che cos'è l'S con il cappuccio?
Sì, allora ve lo dico in italiano che forse è più semplice. Allora, nel caso dello scattering modeler abbiamo elettrone su elettrone, ok? Ed è sperimentalmente tu questo lo puoi realizzare facendo un fascio di elettroni su un bersaglio atomico, in cui vai a beccarti per esempio l'elettrone atomico del bersaglio, va bene? E quindi puoi calcolarti in modo molto preciso l'energia del centro di massa, quindi radice di S per questo caso. Nel caso dello scattering quark-quark questo non lo puoi fare perché non puoi produrre un fascio di quark, né tantomeno un bersaglio di quark. Quello che puoi produrre è un fascio di hadroni che va a sbattere su un bersaglio di hadroni. Okay? Quindi quello che puoi regolare tu sperimentalmente è l'energia del fascio, nel caso di un processo a bersaglio fisso, o l'energia dei 2 fasci nel caso di un collider. Ma in ogni caso tu stai regolando l'energia del tuo hadrone, non del quark che andrà poi a interagire. Okay? Quindi l'energia nel centro di massa per un collider protone-protone, per esempio, sarà ben diversa dall'energia nel centro di massa dell'interazione a livello elementare tra un quark del primo protone e un quark del secondo protone. Ok? Vedremo la settimana prossima, quando parleremo della struttura del protone, come ottenere essenzialmente S barra da S. Ok? Quindi S sarà l'energia del centro di massa al quadrato della collisione protone-protone, ma quello che ti interessa a te è la sezione di tutto elementare quark-quark. Quindi deve avere una frazione, ovviamente, della tua energia totale nel centro di massa nella collisione tra protoni o tra hadroni. Ho chiarito la domanda?
Sì.
Non sembri molto convinto.
Sì.
So. Ok, ripeto, questa parte qui...
l'energia... Provo un attimo a ripetere se ho capito.
Sì,
È
sì, sì,
l'energia
vai,
del
vai.
centro di massa dei due quark che interagiscono. Però
Esattamente.
non la riusciamo a trovare, ma dobbiamo operare sull'energia degli hadroni.
Sì, perché tu, cioè, sperimentalmente
Perché
hai
noi
due
abbiamo
fasci di
solamente
protoni.
quelli su cui possiamo lavorare nei collider.
Esatto, ora scopriremo, diciamo, dopo la pausa di 5
Ok,
minuti perché non è possibile fare un fascio di quark. Ok?
ok.
Va bene. Comunque, ripeto, questo concetto qui lo riprenderemo la settimana prossima quando parleremo della struttura del protone. Poi. Va bene, dunque sono le... Dai, ci vediamo alle 12:15, ok?
Va bene.
Riprendiamo alle 12:15.
Va bene.
Ok, riprendiamo, ci siete?
Sì, ci sono.
Ok, siete in 4 oggi, ma vabbè. Allora, abbiamo adesso visto in dettaglio come calcolare le correnti quark-gluone, come calcolare l'elemento di matrice per il caso di uno scattering forte, quindi mediato da gluoni tra quark, e come le varie combinazioni di colori intervengono nei vari processi, come vengono tenuti in conto, quindi di fatto banalmente alla fine con un numero medio, un valore medio di questi fattori di colore. Allora, adesso andiamo a discutere più in dettaglio di un aspetto molto importante della QCD, che è il confinamento. So, as soon as quarks were proposed by Gell-Mann and Zweig in 1964 to interpret the regularities of hadrons, as we've seen, so the multiplets, many experiments were performed to establish experimentally the existence of quarks. Okay. Now, the searches for free quarks were conducted either at accelerators with any kind of beam particle, so using hadrons, muons, neutrinos, photons, whatever, and also in cosmic rays. And they were also searched with the Millikan type experiment, you know, the oil droplet. And this was ideally an easy experiment because one could easily recognize a fractional electric charge, you know, this 2/3 for the up type quarks and -1/3 for the down quarks. Okay, so this would be easy to find in a Millikan type experiment. And people were searching for free quarks even in substances ranging from the oyster shells and the moon rocks. Oyster shells sono i gusci delle ostriche. Cioè la gente era disperata, ok? Hanno cominciato a cercare questi quark in tutti i modi possibili, anche nei modi più disperati e disparati. Niente. All the searches failed. And this led to the wrong conclusion that quarks must be extremely massive and very tightly bound into hadrons, so that it will be very hard to kick them out of hadrons. Okay. So there were tens of these experiments searching for quarks. None of them found quarks as free particles. And so the wrong conclusion is that they must be so massive and so tightly bound that it is extremely difficult to kick out them of hadrons. Now, today, we know that things are different, okay? As we shall see next week, the existence of quarks inside hadrons is experimentally established by deep inelastic scattering experiments, and this we will study in detail next week, okay? And the experimental evidence are actually consistent with quarks being light and quasi-free point-like particles, so in complete antithesis with the original hypothesis of massive and strongly bound particles. So all this will be clear next week, okay? So, how can we explain the non-observation of free quarks? This is explained in QCD by the hypothesis of confinement, which tells that colored objects are always confined into color singlet states that are the hadrons. You remember, hadrons are white, are colorless, okay? So color singlets. And no objects with non-zero color charge can propagate as free particles. So essentially, no isolated color charges can exist. This is why you can never find them experimentally as free objects, okay? Now, the color confinement is believed to originate from the gluon-gluon self-interaction. You remember the 3 or 4 gluon interactions, which, if you remember, in turn is a consequence of the fact that gluons themselves carry color charge, which in turn is a consequence of QCD being a non-abelian theory. Okay. However, here I'm using here a believed or hypothesis. In fact, there is at the moment no formal proof of the color confinement. Okay, we have experimental evidences, but we don't have any formal proof from first principles. So starting from the QCD Lagrangian, for instance, of the color confinement. And the reason is the following. Confinement regards a QCD regime where the strong coupling becomes very large. So if you remember, the electromagnetic coupling, so the fine structure constant, is not actually a constant, but is a running constant, if you remember, okay? We discussed this with the vacuum polarization, the Lamb shift effect, etc. And the same applies, but to an even stronger extent, to the strong constant, okay? So the confinement deals with a region of QCD where the coupling constant is extremely large, is of the order of 1, compared to 1 divided by 137 for the instruction constant, okay? And so if you have such a large constant, you cannot use this as a small quantity in a perturbative approach. So essentially, when you work in a regime of QCD where alpha strong is so large, you cannot use perturbative techniques. And since you cannot do those, as we have done, it is done clearly and very successfully in QAD, then the theory becomes essentially not predictive, okay? So in this regime, non-perturbative QCD, analytical calculations are extremely complex, not to say impossible, and the theory becomes not predictive. So you can make guess, but you cannot make formal proofs from first principles in this regime. Let's consider, in fact, what happens when two free quarks, suppose a quark and an anti-quark pair, are pulled apart. So the interaction between quarks occurs through the exchange of virtual gluons, as we know, okay? So suppose we are now trying to stretch a quark-anti-quark pair, okay? We want to separate them. Now, the two interact through gluons, of course, one here, one there. But since gluons carry color charge, they are attractive. There are attractive interaction between these two exchanged virtual gluons. And these interactions are mediated by further soft gluons, you see here, okay? And gluons can interact within themselves, so this is allowed only in QCD. So these two original gluons are attracted each other by these attractive gluon exchange in between. So the effect of this attractive interaction is to squeeze the color field between the quark and anti-quark into a so-called color flux tube, okay? So when the distance between the quark and anti-quark is sufficiently large, then the color flows in this way, in such a flux tube. Now you see, close to the quarks, okay, the field line tends to concentrate, but when you are far away, so in correspondence to a sufficiently large separation between quark and anti-quark, the color lines are essentially constant here, okay? They're straight. And so at relatively large distance, the energy density in the color flux tube is constant. And therefore, since the energy density is constant, the energy stored in the tube must be proportional to the separation. Okay, energy density is the energy divided by the separation. So the energy itself stored in the tube must be proportional to the separation of quarks. And this results in a term which is linear in the separation, in a strong potential. If you remember, this kind of potential we've seen yesterday when discussing the charmonium and the bottom state. So you can solve the Schrödinger equation with a potential that has, at small distances, a Coulomb-like term, but at large distance, a linear term, such as this one here. The constant K, it is called string tension, and it is found experimentally to be of the order of 1 GeV over Fermi. And this value corresponds to a very large force of the order 10 to the 5 Newton between any two unconfined quarks. So this is the reason why you can never be able to separate two quarks apart, and so to observe free quarks, okay? So since the energy stored in the color field increases linearly with the quark distance, one would need an infinite amount of energy to separate a quark-anti-quark pair to infinity, which is clearly impossible, okay? And therefore, the colored object cannot be observed as a free object. This is the sense of the confinement, okay? And instead, they tend to arrange themselves into bound states that are overall colorless combination of quarks. So color singlets, which are the hadrons. For instance, this can be, for instance, I don't know, a proton. You see, we have all three possible colors, red, blue, and green. So overall, this is a white object. White means colorless, and since it is colorless, it can propagate as a free object. If you try to pull out one of the quarks which carry color, you will never succeed in this because there is a stronger force that increases together with the distance, okay? So the color confinement hypothesis implies that only color singlet states can propagate as free particles. And this is why all these experiments searching for free quarks actually failed. Okay. Now, in particular, let's consider the case of mesons. Okay, mesons are color singlets with a totally symmetric color wave function. So the wave function, the color component of the wave function of mesons is totally symmetric in this way: red plus red, green plus green, blue plus blue, plus anti-blue. Sorry. And these arguments can be extended to combination of 2 and 3 quarks. Okay, so the combination of 2 color triplets would result in a color sextet and a color triplet. If you remember, we have the same kind of result when we try to combine the 2 flavor triplets. Okay, in SU3. So now we have 2 color triplets, red, blue, green, and you obtain at the end, in group theory, a sextet and a triplet. But you don't obtain any singlet here. Okay? So the absence of a color singlet for a 2 quark system implies that the bound state of 2 quarks are always colored objects, and therefore cannot exist in nature. There is no way in nature you can find the bound state of 2 quarks. Okay, you can find, of course, a quark and anti-quark, because then you have a singlet here, but not from 2 quarks. What about baryons? Okay, the combination of 3 quark triplets corresponding to baryons yields to what? To a colored decuplet, 2 colored octets, and a color singlet. So again, it's the same algebra that we found when combining 3 flavor triplet in SU3 flavor. Okay, so again, we have a decuplet, 2 octet, and 1 singlet. But now we have a singlet. This is exactly what we want. Okay, the color singlet means a white object, colorless. Therefore, the 3 quark system can exist in nature. These are our baryons, okay? And they come with this kind of color component of the wave function, okay? So we have all these combination of colors with the proper signs. And if you look carefully to these to the color component of the baryon wave function, you realize that it is totally antisymmetric. Okay, you exchange 2 of those, you obtain an opposite sign. And since it is the only one possible for baryons, because all the other combinations are colored, then it follows that the color component of all baryons wave function must always be antisymmetric. And this is, if you remember, what we have anticipated when we derived the wave function of baryons, for instance. Okay. If you remember, for the low-rank state, there was a symmetric spatial component with L equals 0. We assumed for that moment that the color wave function was antisymmetric, and now we understand why. And then as a consequence, the speed and flavor must be altogether symmetric in order to get an overall antisymmetric baryon wave function. Now, what about gluons? Also gluons, since they carry color, they must be confined inside hadrons. And this is another fundamental difference with photons, okay? Because photons, they are chargeless, okay? And then they can propagate freely with an infinite range, okay? So the range of electromagnetic interaction is indeed infinite. However, gluons, okay, which are also massless, so they also move at the speed of light, but being colored, they are of course confined into a region which is of the size of the hadron, so of the order of 1 Fermi. And this is why the range of the strong interaction is so small, so microscopic, compared to of course, to electromagnetism. Okay. What if nature would have chosen a U3 rather than an SU3 symmetry group for the strong interaction? If this were the case, then we would have gotten an additional 9 gluon, which is completely symmetric in color. So this would be a color singlet. But then if such a color singlet gluon would exist, it would be colorless, it would be white. So it would be unconfined, and so it could propagate with an infinite range, okay, as a strongly interacting photon. Okay, it would be, let's say, a strong copy of the photon. And clearly, in this case, the universe would be a completely different one than the one we have now. Okay. Now, we have seen that we can have colorless quark-antiquark combinations, which are the mesons. We can have colorless 3-quark combinations, which are the baryons. We cannot have a colorless quark-quark combination because this is colored. But in principle, one can also think to different possible color combination, which results in a singlet, in a color singlet. And this was already predicted by Gell-Mann back in 1964. So in principle, there could exist several different color singlet hadronic combinations in addition to the standard baryons and mesons. And these are essentially the types that can exist. So we can have pentaquarks, which are hadrons made by 5 quarks, okay? So d-quark, d-quark, and antiquark. Or dibaryons, which are mesons made by essentially 6 quarks, so 3 d-quarks. We can have tetraquarks, a d-quark, the antiquark pair. We can have molecules, like 2 bound mesons. We can have hybrid, which are a combination of quarks and gluons. And we can have also pure gluonic states, which are glue ball. Okay, and all these possible combinations allow for colorless states. So in principle, as it was already predicted by Gell-Mann in 1964, different hadron types than baryons and mesons can exist in this combination, provided that overall the color is 0. Okay. Now, none of those exotic hadrons had been discovered until, let's say, 18, 20 years ago. But today, more than 30 exotic hadrons have been experimentally observed in many different experiments, although not always their quark-gluon structure is understood and not always the quantum numbers are established. So let me go back to the charmonium, okay? So here we see all the charmonium state. This is all the state below the threshold for the production of 2D mesons, and this is all the charmonium state above the threshold. Now, in yellow, you find those that are experimentally found. So all those below are found, but there are other in the upper part which are not. So these are predicted but not yet experimentally discovered. Okay, and this is just about charmonium. What now if we allow for exotic hadrons in this panel? This is what we obtain. Okay, so red are neutral exotic mesons, and blue are charged exotic mesons. You see how many new elements can be filled in this matrix. Okay, and indeed some of those have been discovered, some other are just predicted but not discovered. And this table summarizes some, the main ones. Okay, so let me tell you that the first one observed is the X3872 MeV. This was discovered by the Bell experiment in Japan back in 2003, so 17 years ago. This is the mass, okay, clearly, which is already reported in the name, the particle name. The width, which is more than 1.2 MeV. The quantum numbers are now well assigned to this object, so it's a 1++ object. And you see also here all the decay modes that have been observed so far, okay, where these objects can contribute. And then we have many others, okay? Some are called X, some are called G, Y, Z, etc. Okay, you see sometimes the quantum numbers are not established. These are even more other examples, and there are several more. Okay, this table is not complete, but it gives you an idea that it is now a very recent field. Okay, in particle physics, the search for new hadronic exotic hadrons, essentially. Okay, let me give you some example. Okay, so first of all, the pentaquarks. After more than a decade of controversial results by many experiments, okay, that claimed the pentaquark discovery, but then they had to change mind, okay, so at the end they say, oh no, this was just a statistical fluctuation. Then the existence of pentaquarks was finally confirmed by the LHCb experiment at the Large Hadron Collider in 2015, okay. In particular, 2 highly significant resonances were discovered in this decay. So the decay of a lambda B0 baryon, which is a baryon with a bottom quark, up quark, down quark, into a K- and this pentaquark. As you see, the decay is regulated by the weak interaction, charged current weak interaction. This will be studied, of course, later in the course. And so you start from a BUD quarks, and at the end you obtain an SU bar quarks, which combine into a K minus, and a UUD CC bar 5 quark system, which is our pentaquark, that further decays into a proton and a JPSI meson. So this is the result that has been published in 2015 by LXCB. Okay, you see here the invariant mass of the JPSI proton system overall. So this is overall together with background. But then when you subtract the background, you obtain essentially these two structures here that are clearly visible also there, of course. So the first one at lower energy is this. The one is the pentaquark at 4,380 MeV. The quantum numbers are 3½ minus. The mass is this one, and the width is order 200 MeV. So it's quite broad. Okay, and you also see here the significance of the discovery. You know that in order to claim a discovery, you need a 5 sigma significance, and this was 9 sigma, so well beyond the threshold for claiming the discovery. And the other one is just a little bit more heavy. Okay, the quantum numbers are 5½ plus. The mass is a little bit higher, and it is more narrow. Okay, so the width is only order of 40 MeV, and the significance is even higher, so order of 20 sigma. Now, a richer structure, okay, was very recently observed by LXCB in the same channel after now analyzing the full data available. So all the data collected from 2011 up to 2018. Okay, so you see here a Darius plot for this decay, much like the one we discussed yesterday. Okay, when as a tool to search for resonant intermediate states. Okay, and you see here that there are two lines, one here in the squared invariant mass of the JPSI proton. One is narrow, one is a bit broader. And then when you perform the full analysis, which was a very complicated analysis, a multi-dimensional analysis, a very, very complicated one, okay? Then last year, so 26 March 2019, this new paper was published by LXCB, where now the bump, one of the bump before is actually resolved into two contributing states, okay? And this corresponds to this stronger line here in the Darius plot, okay? So the PC 4440 and 4457. And then a new state, a new pentaquark state was also discovered with a significance of 5.4 sigma, okay? Just below there, below this mass, okay? And then there are, of course, many hypotheses on the structure of these objects, okay? It can be, of course, a truly pentaquark object, so with the up, down, charm, anti-charm system. Overall, clearly, this is colorless, okay? So we have a red, blue, green, and then let's say red, anti-red. So overall, this is white, okay? Or this can be essentially a molecule, okay? So a molecule given by either a D0 or D0 star meson together with the sigma C plus baryon, okay? And the quantum numbers will be different in both cases. So this is still, of course, under debate by the theoreticians. What about tetraquarks? Okay, recently, also new evidences of existence of C bar, S bar tetraquarks have been reported by the LXCB in the attempt to interpret 4 exotic resonances which are produced in this decay. So this is now a B plus meson, as we studied yesterday, decaying into a JPSI, a phi meson, and a K plus. Okay, and when you look now at the invariant mass of the JPSI phi system, here the LXCB collaboration found these 4 structures here. Okay, these are embedded together with the background, but when you subtract the background, you see now these 4 very significant peaks. And these are, in fact, the data that we have. So these are the 4 masses of these exotic object, is a tetraquark. These are the quantum numbers, most likely quantum numbers. There are also other possibilities. The widths and the significance, as you see, in all cases, this is above 5. Okay. So I think this was the last slide. Yes. Ok. Domande? Tutto chiaro?
No, sì, va bene.
Sì, abbastanza
Ci
chiaro.
sono.
Grazie.
Ok. Benissimo,
Tutte
benissimo.
queste strutture sono molto rapide a decadere.
Sì, chiaramente, cioè le crei e immediatamente decadono, infatti li osservi come risonanze, non riesci a tracciarle con un rivelatore. Sì. Va bene, allora ho fatto l'esempio di l'HCB, ma chiaramente diciamo, queste stesse ricerche si fanno dappertutto, anche a CMS e Atlas ovviamente per quanto riguarda il CERN, ma anche a Bell 2, che adesso è l'evoluzione di Bell in Giappone. Alcune di queste strutture si studiano anche a più bassa energia a BESS 3, che è l'esperimento in Cina, a Pechino. Alcune delle più leggere si studiano anche al Jefferson Lab negli Stati Uniti. Okay? Quindi chiaramente tutto il mondo, una volta che si è capito questa cosa, si è mobilitato per andare a cercare nuovi stati isodici e possibilmente anche interpretarne la struttura e ottenerne i numeri quantici. Va bene, se è tutto chiaro per oggi ci fermiamo qui, ricontinuiamo domani. Domani completeremo il capitolo della QCD, parleremo di diversi altri aspetti importanti della teoria. Niente, vi chiedo soltanto domani di connettervi puntuali, cioè quando abbiamo lezione alle 9 cercate di essere tutte le 9 già connessi, così partiamo subito. Ok?
Nessun problema.
Va bene, sì.
Benissimo,
Grazie.
arrivederci allora a domani.
Arrivederci.
Arrivederci.
A domani.
Sì, buona.
A domani.
Interrompo la registrazione adesso.